goes, looking at setups, better ways to improve things and ultimately provide more value at the spindle for their customers. I've been with SGS for about 2 years now. July will be my 2-year mark. I have 16 years of experience in the industry as a whole. The 14 prior to SGS was split between the aerospace world and the firearms industry. I started out as a machinist in the Air Force, did that for not quite 10 years, and then got out and went over to the civilian side of things. I am based in Fort Worth, Texas, but I travel the entire region pretty regularly. So if I happen to be out in some of your area, feel free to reach out and we can set something up. I'll let you know when I'll be out. So let's jump in. Steels, that's a pretty broad category, pretty generic statement, right? There's a lot that's encompassed there. We're going to focus in on carbon steels, alloy steels, and tool steels. If you happen to have attended our previous webinar that was focused on stainlesses, then we've already covered that. So we're going to dive into the other items. Carbon steels, alloy steels, and tool steels are dictated by their hardness and their elemental makeup. As already mentioned, that is still a wide variety of materials and ultimately a really wide variety of machining characteristics. When you have a group that ranges anywhere from 86 on the Rockwell B scale all the way up to 68 on the Rockwell C scale, that's a lot that you're kind of encompassing and a lot of considerations to be made. And then you also have designer materials like hard ox or AR 400 or 500 armor plate. There's just a lot to kind of unpackage there. And so tool choices become really critical when you're looking at this kind of a variety of materials. And you also have to look at your machining environment. Are you a production shop that's going to be running, 10,000 a quarter of this one part, that's this one material? If so, then you may look at a very specialized tool that's most ideal for your particular material and application. Or you may be a job shop that takes on, 5 of this part and this material, 10 of this part and a completely different material, and then a small run of 50 or 100 of something else. So then you may want to have something that's a little bit more middle of the road that's going to provide you a good bang for your buck in all of those applications. So again, there's just a lot to cover and a lot to kind of take into consideration. So for carbon and alloy steels, composition is the key here. They are designated by their material or elemental makeup and then the carbon content. The first 2 numbers denote the alloying elements, and the second 2 are the carbon content in hundredths. So if you see like a 4340, then you'll know that the 43, that's a chromium molybdenum blend with a 0.4% carbon content. So it gives you a good idea of what you're going up against and kind of how to plan for that. As already mentioned, machinability will vary a lot as that carbon content increases or decreases, and as you add different elements in or take them away. Sometimes you'll add in things like lead or sulfur to improve the machinability, but that can also be viewed as a lower quality in the material itself. So, again, it's all about figuring out what's in front of you, what you're having to work with. So here's a list. You'll see some of the items. We're not going to go through the whole thing, but depending on what's added in, it may increase hardenability, machinability, as already mentioned, corrosion resistance, even potentially the electrical and magnetic properties of the material. So this is the crux of it. So the more you know about what it is you're cutting, then the more you can plan. Do you need a material or a tool that has more shear because you're running something that's really gummy or doesn't like to make a chip? Or is it hardened and you need something with, a more robust edge or whatnot? So this plays a big factor into picking what you're going to run. Then tool steels, and they run along the same lines as carbon and alloy steels because they are carbon and alloy steels. They just have additional characteristics like hardness or wear resistance, toughness. All of these at elevated temperatures. That's the key there. They're steels made for different types of tooling, whether it be stamping or shearing or cutting knives, whatever the case may be. They're purpose-driven materials. And you may even see some that have cobalt or nickel added to them. And that really is going to help them push even higher performance at higher or more elevated temperatures. So machinability, you've mentioned that a couple of times already. Machinability is defined as how easily a material can be machined using a cutting tool. But what we're really just talking about is how easy does that tool or that material make chips? How easy is it to cut that material? And that changes, as we've already talked about with adding different elements, higher carbon contents make them harder and all these things. So we track that with a machinability chart or machinability rating. And this is really just more of a reference than anything else, but it's based off of 1212 carbon steel. Being 100%. So that's your standard for machinability. Anything that's easier to machine than that is going to be over 100%. Anything less is going to be less than 100%. So you can look at a few examples there, like 43 or 4130 is at 72%. You go to a tool steel like D2 and it's at 27%. So kind of gives you an idea with known variables. Say if you machine 4130 a lot, you can see that it's at 72, and then all of a sudden you go and you need to run, an O2 or something like that, then you'll know that it's, a little bit less or a little bit more than half the machinability of 4130. So it's just kind of, again, a reference thing. Ultimately, though, the material composition, the hardness, how it was produced, if it was cast or forged, or if it was made out of wrought or billet material, and even other processing methods like flame cutting or welding, laser cut, anything that'll change the temper or create a heat affected zone over certain portions of the material. Those are going to play major factors in machinability. And that's the central aspect of the decision-making process and what cutting tools to use. So decisions, it's steel, just throw a 4 flute in it and hit the button. Well, that doesn't always work. When you look at it, of course, there's a lot of variables. Do you need something with higher shear? Are you pocketing? Are you profiling? Are you going to run it dry, or are you going to run flood coolant or through spindle coolant? Do you need a chip breaker or continuous edge? These are all considerations to be made in trying to nail it down and say, okay, is this the right tool for my application? And ultimately, that's what it is. What best suits what you're doing? Do you need a reach tool, for hardened steels, or a ball nose, or, a multi-fluted finishing tool? What is the best thing for your application? And so then there it is. It's the right tool. Now, the right tool doesn't really exist. There are tools out there, some better suited for things than others. But there's not always the perfect tool for whatever it is that you're doing. So you have to analyze what you have available to you and figure out if it suits your needs. The main categories that we look at there are substrate, geometry, coatings, and then the tool paths that we're going to be running it in. So we'll dive into substrate. Substrate is pretty straightforward. I mean, this is the actual carbide itself. And essentially all it is powdered tungsten carbide held together with a cobalt binder. Now you'll see other alloys added in for different things like corrosion resistance or thermal stability. But ultimately, it's that percentage of that binder that really affects the performance of the tool. So the less binder you have, then the higher heat capacity that tool is going to have. It can withstand higher temperatures of operation, and it's also going to be more rigid. There's just not as much flex in the tool because it's more carbide. And the more binder you get, the higher durability that tool is going to have. It'll have a better tolerance to repeated shock. If you're not running it in really difficult to machine or very hardened materials, then a lot of times that'll equate to better tool life for you. And a note on that, all of SGS's mold and die tools are based on the lower percentage of cobalt binder. So this is just, based on adding some rigidity, adding that heat capacity, being able to handle the stress and heat generated in those difficult to machine materials. So what does the geometry look like? What are the considerations to account for there? So radial rake and helix angle are going to be the major factors as far as how that tool cuts in whatever the given material is. Rake angle is going to play the largest role. That negative, neutral, or positive rake angle is really going to affect how that chip is created, that wedge that's actually producing the chip, and then subsequently how that chip flows off into the flutes and then away from the cut. The angle itself is going to generate certain cutting forces. A positive geometry is going to create less force than a negative geometry is. And with that force comes temperature. So the more force involved, the more heat that's going to be generated. And then ultimately edge strength is the tertiary factor there. So as that positive angle goes up, that strength goes down. As it goes down into the negatives, neutral to negative, then it's going to get stronger and stronger. And ultimately, that's the key. It's finding a balance between that power and then the edge strength. So the higher the angle, the less power is required to run that cut. It's going to cut more efficiently. You can run it on a lower horsepower machine or a lighter setup, and you can get good results out of it. But it is going to have a lower strength, so it's going to be a sharper, more brittle edge that can fail. And so this makes it ideal for higher machinability materials. Lower angles in that neutral into negative territory are going to be about edge strength. They are going to require more power, but they're going to have a significantly stronger edge that's going to handle just more abuse ultimately. But like I said, it will take more power, a little bit more horsepower requirement on the machine, and or more rigid setups to be able to take the force behind that cut. So this will be ideal for tool steel, mold and dies, as well as some of your high temp alloys, a lower positive to neutral, maybe even into negative geometry can be beneficial in some of those as well. Next up is helix angle. So helix angle it plays a couple of different factors here. So it helps with getting the chips out and away from the cut, and then ultimately up and out of the part. It also acts as an aid in the shearing action with the radial rake. So, by increasing that helix angle, you add extra shear, which makes the cutting movement a little bit more efficient, a little bit more effective. But as you increase that twist, now you're going to have more flutes in contact with the material at one time. So now you have extra contact, potentially need a little bit higher horsepower requirement or a little bit more rigid setup. So those are things that you kind of have to balance out there. That degree of helix will also add some rigidity into the tool as you get lower into low helix or even straight zero helix. You're going to have a much more rigid tool than something with a really fast twist. So this is all about balancing out tool stability, workpiece contact, and then also that shearing action. That's the goal, but you can't lose out too much on either side. So how do you effectively do that? And it's based around a combination of the two numbers. So when you look at your normal rake angle and your helix angle, they actually come together to create a dynamic rake. And so you can use this balance between the two in order to get a more effective cutting geometry while boosting rigidity or edge strength. So you take a tool with a low positive rake, put it with a higher helix like our series, our T-carb, which is our 6-flute kind of high efficiency tool path driven tool that has a low positive rake and a 41-degree helix. And you can get a really good shearing action out of it, but still maintain a really strong edge that holds up well in high temp alloys and things like that. So, it gives you kind of a blend of both worlds. On the other side of that, you can take a really high positive rake, put in a slower helix, and you can get a really good clean cutting action with a very, very rigid tool. This is a good example of this is our multi-carb. So It's going to be basically a dedicated finishing tool, but has a really high positive rake, a really low helix angle. So with the core diameter on it, with having a really high flute count, on top of that slow helix, it's just an extremely rigid and stable tool. So we use this a lot throughout our product line in order to give that balance of, best performance across multiple mediums. Next is relief type and the flute count. So when you see a relief type, typically you're going to see eccentric or faceted. Eccentric is going to be down here on the left. You'll see it's an arced grind coming back away from the cutting edge. So this is going to keep a little bit more material behind the cutting edge, which is just going to beef it up a little bit, give it a little bit more life, a little bit more support, as opposed to a faceted, which is a flat grind that drops off behind the cutting edge, and then it drops off again traditionally into a secondary relief. Both have their places. It's just a matter of utilizing them to the maximum benefit. A faceted relief is going to have a really sharp edge, so it's great in finishing operations or lighter materials to machine. And then the eccentric, you're not going to have quite as sharp of an edge, but you're going to have a much more durable edge. So you can run that in more difficult to machine materials with a little bit better tool life out of it, typically. Flute count. Now this is one that people will argue about for hours upon hours. What's the best number of flutes? Is it a 4 flute, a 5 flute, a 6 flute, a 37 flute? People have their flavors and they like to stick with them. But ultimately, there is no right answer because it all depends on what you're trying to do. The flute count plays a big factor in the amount of chip space. So that's how much your flute can actually handle as far as the size of the chips going into them, as well as tool contact, and then core diameter and harmonics. So with higher flute counts, you're going to have a larger core diameter, and that's going to help tune out some of the resonance that's in the tool itself. You couple that with an odd number of flutes, and that's going to tune it out even more. So you end up with a really stable tool traditionally when you go to a higher flute count. Higher flute count tools tend to be better suited for high efficiency machining or finishing tool paths. That chip space you can see here on the right, there's a much smaller amount of area for the chips to go versus a 3 flute over here. So you can use those types of tool paths with lighter step overs, a little bit more aggressive rates, and usually longer lengths of cut, and get some really good metal removal rates out of them despite using a lighter step over. On the other side of that, you go to a lower flute count tool, and those are going to be better suited for, or traditionally better suited for, aggressive tool paths like slotting or even constant step overs where your tool engagement may spike as you're going into corners or contours or whatnot. And it just boils around that having that chip space, that tool is capable of handling those types of cut more effectively. A good example of that is our Series 33. It's our 3 flute. It is designed for stainless steels, high temp alloys, as well as some of your more difficult to machine steels and generic steels as well. The design of it really helps, especially when it comes to slotting and tight pocketing or really tight corners, because you have fewer flutes that are contacting the workpiece. So it lowers some of that stress when you go into those corners. And it shows itself in how the tool runs as it's navigating those tool paths. So what does that look like when you start comparing geometries from different tools to one another? Here's a video. This is the first tool is our Series 1. It's a general purpose 4 flute. It does have variable indexing, so that's one layer of chatter reduction. And you're going to see it compared to our Z-Carb AP, which is another 4 flute, but it's a high performance tool. It has variable indexing as well as a variable helix and a variable rake. So it has 2 extra layers of chatter reduction. You'll see them at a 25% step over, a 50% step over, and then some more aggressive rates. And just pay attention to the tonality and you'll really hear the difference between the two. So as you can see, there's a big difference in how those two tools are handling those cuts, particularly the increased rates at the 50% step over. The general purpose tool, it runs the cut, and it'll certainly do the job, but you can hear how much better the high performance version, the Z-Carb AP, how it handles that cut more efficiently. It's almost as if it was designed for that. But that's the key is, when you look at different applications, certain tools are just their configurations are really just enhanced to be able to run in those more effectively. Next up is coding. So coding is going to work by complementing the cutting tool. It's going to take whatever your tool was originally doing, and it really just enhances that. So increased surface hardness, preventing adhesion, resistance to oxidization, adding lubricity into the cut, and then of course providing a thermal barrier between the substrate and the workpiece. You can see the chart here. This shows an uncoated tool at various heat points compared to coated tools. And I mean, there's a pretty drastic difference there. So when you start thinking about running a tool, especially like with this Al-10 coating or TA coating, and more difficult to machine materials, you gain a lot of performance there because you can operate at higher temperatures and for longer periods of time. Not to mention, uh, as shown down here, you can see the buildup on the edge. So this tool is really starting to build up on the front edge. So now it's really pushing instead of shearing, whereas the coated tool doesn't have any buildup at all. It's just going through and shearing exactly how it was designed to do. So over time, this is going to start to build up and break away, which can actually pull substrate along with it. And it's going to cause that tool to fail prematurely. So you gain a lot of benefits from coating, and a lot of times it's just figuring out which coating is more ideal for what it is that you're doing. So here you'll see thermal imaging, a difference between an uncoated Series 1 and 4140 versus a Dynamite A, which is an Al-10 coating in the same material. At first glance, you see that the coated tool looks like it's heating up faster. And it's actually supposed to. So what's happening is that heat buildup is being spread across the surface of the coating. Whereas on this tool, it's isolated strictly to the cutting edge. So this coating is doing its job and it's providing a barrier to the actual substrate. So as this gets hotter and hotter, eventually that substrate is going to start to break down, which your cutting edge is going to break down, your tool's going to dull, and eventually it's going to fail. Whereas this coating will allow this tool to operate more efficiently, again at higher temperatures for longer periods of time, because it's providing that barrier. It's spreading that heat out across its surface, and it's ultimately extending the life of your tool. Now we're going to look at tool paths a little bit. And this is something, we could have an entire webinar series just on toolpaths. So we're not going to get too crazy into that. But when you look at part geometry and your chosen tool paths, they're very critical when selecting tools, or vice versa. If you already have tools, then getting the right tool path for the type of tool that you have available to you is really critical. High efficiency milling and tricoidal tool paths use constant cutter engagement to benefit from high fluke count tools with long lengths of cut at higher rates of feed and speed. I've already kind of touched on that. And the same thing inversely for constant step overs. They generally perform better with lower fluke count tools with larger chip space and less fragile edge geometry. Here's an example of that. So on the left side here, we have a constant step over tool path. This is a 10% step over, but you'll notice every time it hits this corner, it essentially does a full slot. So it's not doing 10% anymore because your cutter engagement has now spiked, as opposed to a constant engagement where you're taking 10% each time and it's scalloping across there. So with a higher fluke count tool, you can run this at higher rates of speed, longer axial depths, and you can run it very efficiently because the amount of pressure on that tool stays the same all the way through the cut. As opposed to over here, you would want a lower fluke count tool. You wouldn't be able to, or wouldn't want to run as deep of an axial step over, and you'd probably run it at lower rates to account for that little slot going in there. Something like our Series 33 or the Z-Carb AP would perform the cut, but you would definitely have to make sure that everything is dialed in to account for that particular portion of the cut. So there's more thought that may go into it. It's not quite as set it and forget it in some cases as a constant engagement can be. So when we look at engagement, engagement's controlled by two different things: radial step over, or radial width of cut, and then the tool path of the cutter. So as you increase your step over, your tool engagement is going to increase. You can see here, this is a 10% step over-ish, and you're going to have about 45 degrees of tool engagement, as opposed to a 50% step over, where you're going to have 90 degrees of tool engagement. And then down on a full slot, you have 180 degrees. Your tool's fully engaged. So you're going to, as this increases, you're going to have more pressure on that tool. It's going to require your spindle to have more power to be able to turn it efficiently. And those are things that you have to look at as far as setup rigidity and the actual output of the machine and things like that. You also have to take a look at what the tool path is. So this same 15 to 10% cut here, you got that a little bit more than 45 degree tool engagement there. But as you start to run it into contours, your tool engagement spikes. So you're going to have a tool that's running at a rate that's for a lower amount of engagement. So this tool can bog down in these corners, and it may fail, but at the very least, it's probably going to chatter some, and you're not going to get the finish that you're looking for. The opposite is true on the outside. So as you come around here, you're going to get less engagement. Your tool's not going to be cutting as efficiently. And so you're going to get some rubbing or potentially even some skipping across the corner there because the tool just isn't biting into the material anymore. So here's an example of that. On the first half, you'll see a straight path. You'll be able to hear that constant engagement all the way across. It's just a nice solid hum. Then the second part, you're going to see it moving in and out of some curves. And so when it hits the inside of those curves, you're going to hear it, squeal a little bit. And, if you were to look at this part once it's done, you're going to have chatter marks in there that you're going to have to worry about cleaning out and whatnot. So that was a 32% spindle load all the way across the board there. So in that toolpath, we have a 24% load on the outside and a 48% load on the inside. So, there's a pretty wide range of loads, and depending on the material that you're cutting, that can get even more drastic as far as that spread goes. So that can play havoc on your machine over time, especially if you're running those parts for extended periods of time and whatnot. It can start to wear out bearings and axes and things like that. And it's just something you have to keep an eye on, as opposed to running a constant engagement that'll go in and whittle out those corners and keep it more consistent across the board. So which is better, constant step over or constant engagement? And the truth is, neither one is necessarily better. It just depends on what your part looks like and what your machining environment is. If you're running a light duty machine that has faster axial movements, then you might run more constant engagement tool paths or dynamic tool paths or whatever you want to call them. To utilize the speed of the machine and to account for the lower rigidity of it. If you have a really sturdy, rigid setup, then you may run more constant step overs so you can get the best benefit out of that solid, heavy machine. I spent all that money on Mastercam, so I'm going to dynamic mill everything. I get it. CAM softwares aren't cheap. You want to use every feature that they offer you to get the most bang for your buck out of it. But sometimes using some of those features actually sets you back a little bit. And here's a good example of that. So there you go, almost twice the amount of time involved to do a dynamic tool path as opposed to a standard offset, heavy 400 thousandths, on a half-inch tool step over. Now, if you look at the cost per chip there, you're going to gain out a lot by going with that standard offset method. But that isn't always the case. Now you take this operation where now instead of 3/4 inch deep, we're doing 1 inch and 200 deep, and we're having to do that traditional step over in 2 steps, and it's a different story. So there it is, 4 seconds, over 1,000, 10,000, whatever parts that you're doing annually, that can make a large difference. And this is on really simple geometry here. You get into more complex features, and that's going to play a much larger role. But the point is just to highlight that, depending on what your part looks like and what you need to cut, sometimes the high efficiency method is not always better. But then there's plenty of opportunities where it is. So we'll jump into some troubleshooting things here. Hopefully everybody has at least broken a tool once. If you ain't breaking it, you ain't trying. Hopefully you haven't had one that's loaded up as bad as this guy is, but that's aluminum, obviously. It's kind of tough to get one quite that loaded up in steel, but it does happen. And ultimately, when you see this kind of buildup, it's generally going to result because or be a result of your spindle speed being too low or not feeding hard enough, as well as or coupled with a dull cutting edge. Coolant plays a factor in it. Sometimes the cutter geometry, like the hone, um, will be a factor as well as not having the right rake or clearance or whatnot. But generally, it's going to boil down to rates, a dull tool, or not having coolant where it should be, or air even where it should be. So you can try increasing your feed rate, then play with your RPM. Make sure the tool's not worn. Get your coolant positioned how it should be. The most effective way possible to be in around the entire cut, and then you can also look at playing with different geometries and different coatings if that doesn't work. Corner chipping. Uh, Traditionally, this is going to be an issue caused by too high a feed, the corner being too sharp, or just not having rigidity in your setup, whether it be on the part side or the tool side. Too much projection in the tool, too much tool sticking out. Um, you can look at playing with your RPM, getting your chip load down a little bit. Also, if it's a roughing operation or a profiling operation, if you can get away with running a corner radius or a chamfer instead, then that's obviously going to add some extra protection to that corner, allow you to get through the cut, and then come back and finish it off with a square tool. Um, if that's not an option, then like I said, you can play with your RPM, lower your feed rate, get that chip load down, make sure that all of your setups are rigid. If you have an interrupted cut, then slow down going into that interruption. Really, if it's a extended amount of interrupted cuts, then you may just slow down overall and allow it to engage those interruptions a little bit more efficiently. Flank wear. Flank wear is almost always caused by heat buildup. That can be because you don't have a high enough chip load and the tool's just rubbing, or the geometry on the tool puts too much friction or contact with the part, or you just don't have coolant where it is, but where it needs to be. But either way, all those boil down to heat buildup. So you can slow down your surface footage. You can try increasing your feed rate, get a heavier chip that's going to pull the heat away from the cut. You can look at some geometry changes with some more clearance. But a lot of times coolant plays a big factor there. You can just reposition your coolant, check your coolant concentration, or whatnot. And then lastly, you can also look at different coating, potentially the material that you're running in. There might be a different coating that's better suited for that material. Cutting of the chipping edge. This is, there's a lot of different causes for this. You'll see tool run out being an issue, rigidity in both the setup and the tool itself. If your parts bouncing back and forth because your work holding isn't strong enough or rigid enough, um, or your tool has too much hangout or projection and it's bouncing off of the part, that's going to cause chipping because that tool is going to come in and it's going to bite a little bit heavier on one flute and then bounce back out, cut lighter, and then come back in and cut heavier with the next flute. So check your fixturing and your setup. Make sure that any vibration that you can get out of the setup is looked at, whether it's from projection or work holding. Also, check the tool for runout. Just throw an indicator on there and make sure that it's running as true as possible. Um, Side lock holders are notorious for putting tools, in less than ideal runout situations, especially for high efficiency machining. You want to try to stick with, at a minimum, a collet setup, but heat shrink or hydraulic or a milling chuck or something like that. That's really going to help that tool run true. Um, Otherwise, you can look at different geometries, something that's just going to cut with a little bit more robust edge. And you can also look at decreasing your feed rate, lowering that chip load a little bit. But a lot of times it's just figuring out how to tune in your setup. Cratering on the edge. So cratering on the edge almost always is caused by too high of a speed. Um, Ultimately, this is heat and pressure. So you're building up too much heat in one spot on the tool. Um, it could be because your relief is too large. There's not enough meat behind there that's really causing the heat to dissipate through. Um, could be from a coating issue, whether the coating flakes off, you didn't have the right coating, or it could just be an uncoated tool that you should be running coated. Um, feed rate being too slow is usually a good culprit here. That material flowing across that rake face and into the flute is not pulling enough heat away from the material itself. It's not a large enough chip to break away and pull that heat out, so it builds up, and that pressure of that chip running across there slowly starts to wear a divot basically into that rake face. And eventually it's just going to cause it to wallow out, and it's going to crack out on that edge because there's just not enough material there to support it as well. Um, and it also can be caused from a buildup on the edge. It's going to cause the chip to flow into it abnormally, which will cause irregular wear patterns and whatnot, and again will ultimately lead to cracking. So um, you can always try to increase your feed rate, get a little bit heavier cut, get the chips moving through a little bit faster, and get the heat pulling out with the chip, as well as playing with your coolant. Ultimately, if it's a heat problem, coolant can play a big factor in trying to fix that. So you can look at repositioning, look at increasing the concentration of the coolant, or maybe even just cleaning if it's been 7 years since you've cleaned your coolant out. That could be a factor. But all those things are stuff to look at if you're starting to see some cratering on the edge. Land and body wear. Usually this is a spindle runout issue. Not always, but usually it is. And you'll see it in irregular patterns across the body of the tool. So um, one side of the tool is rubbing more than the other is, so you'll see those wear patterns. It can be caused from an interrupted cut, the setup not being rigid, as well as if you have an abrasive material like a casting or something like that that has impurities or potentially even voids in it. And then, of course, like everything else, insufficient coolant can cause issues like this as well. So check your spindle setup, decrease your feed if you're in interrupted cuts. Um, take a look at your coolant situation and see if there's any improvements that can be made there. Don't run crappy castings if you have the option, that is, and then check your coatings. If there is a better coating, or if the coating just is wearing off and it's causing the tool to fail early, then that's something to look at too. Poor surface finish. How do I make my surface finish better? Usually, it's a combination, or individually, the wrong geometry for finishing, or too heavy of a feed rate. Rigidity can be a factor there, but if you're finishing, generally you're not taking that heavy of a cut. So I would hope that at that point you probably have that part dialed out. Um, but it does happen, and sometimes it can just be a worn tool. That tool, it just doesn't have the sharp edge that it did, and so it's just not cutting as efficiently, and it's pushing material now, or rubbing or smearing instead of shearing it off. Um, so the first thing to look at is, do I have the right tool for the job? Is this a good finishing tool? And if it is, then you look at your fixturing and setup. Make sure you don't have too much tool sticking out. Um, if it's not, then you can look at better geometry that's going to give you better shear, better engagement, whatever the case is, wherever you're having problems with that finish, in order to be able to improve it. Of course, lower your feed rate. Finishing rates should not be, overly aggressive, because you want to give the tool a chance to work, and really cut with small movement in between one flute to the next to get that higher quality finish. And then lastly, check your wear. That's going to be a big factor. If you've got a tool that's starting to wear some, just move it out, let it be a rougher from then on, and until it dies, and then put a new finishing tool in. Chatter. So this is the one that I'm sure everybody's seen at least once in their life. You run a tool and everything's running great, and then all of a sudden it starts chattering like crazy. In most cases, this is going to be attributed to having too high of a speed, and your tool is pushing and it's not cutting, or it's rubbing and not cutting. Sometimes it can be a factor of rigidity, both on the tool side and the workpiece side. Another thing it could be is tool diameter. So like in this case in the picture here, having a large diameter tool going in and driving these corners, it's going to have a tendency to grab once it hits this higher engagement in the corner on a larger tool and jump. And so once it starts to jump, it's not going to stop. So you're going to see that run all the way through. It's going to hit this corner again. It's going to basically repeat itself. So using a smaller diameter tool will help with that, because you're not going to have that whole radius of that tool engaged as you're going around that corner. So it's just going to cut more efficiently, and it's going to tune that out. Now, on the flip side of that, you have a really small diameter tool with a ton of flute length. Now you have a flimsy or a less rigid tool. It's going to have more deflection in it. So as you're running these cuts, it's going to push off more, and it could start to bounce some on its own. And that's where those different layers of chatter reduction really come into play, because sometimes you have to use a smaller diameter tool with a long length of cut. So having variable geometry, uneven flute counts, things like that, really help to lower that. And then I've already touched on projection and length. So you can always play with lowering your spindle speed, allowing the tool to bite more effectively and get a better cut into the material, looking at a tool with better shearing properties. Higher rake angle, higher helix, it's just going to cut more efficiently and dig into the part in a good way. And then of course check your fixturing and setup, make sure everything's really rigid, that you're not getting movement in there. I've already touched on the diameter, and of course the shortest length of tool and the shortest amount of projection that you can get away with for your part. Sometimes you have to have that crazy long length, but a lot of times you don't. You can get away with something shorter, and it's just a matter of finding the right holder for it. Catastrophic failure. I don't know. I just turned away from the machine, and next thing I knew, the tool blew up. Um, sometimes you find the pieces in the part, you got to dig them out of the part. Sometimes they're in the chip bin and forever to be lost. So you don't necessarily know what happened. But a lot of the culprits there are things that you can kind of look back at and diagnose. So chip packing. Were you recutting chips? Was there enough room for chips to be evacuated? Was there coolant flow or air flow through there to help get those chips up and out of the way? Was your tool getting worn? If you can see on your finish leading up to that point, if it was starting to suffer, then your tool might have been wearing, and so now it was pushing instead of cutting, and eventually it's just going to fail if that's all it's doing. Was your coolant in the right spot? Did it have constant coolant no matter where it was in the cut? If it goes around to the backside, is there still coolant hitting it, or is the coolant only hitting the top of the part at that point? After a while, that heat's going to build up. It's going to wear that tool. Again, now you're pushing instead of cutting. Speed being too high. Sometimes we just want to try to, get as aggressive as possible. The old saying, push it till it breaks and back off 10%. Well, sometimes that's exactly what happens. You push it until it breaks. So, at that point, you're still pushing with the tool and you're not cutting anymore. You've outgrown or moved beyond what the actual cutting capacity of that tool is. So then it pushes and eventually it fails. And then non-rigid setup. We've talked about this a couple of times with some of the other typical issues that you'll see, and it's just a resounding thing. Is my setup as rigid as possible? Sometimes it just can't be rigid. You might be machining high walls, real thin materials, and whatnot, and it is what it is. But to the best of your ability, is your setup as rigid as possible? And then insufficient power. I think this is one that sometimes gets overlooked. Does my machine have the requirements and output to be able to run what it was I was trying to do? If you're taking, really aggressive, deep axial, deep radial step overs, you're going to need more horsepower on your machine. On the other side of that, if you're taking really light step overs with really long axials and large diameter tools, you're still going to need that power, even in like aluminum. You may get beyond 30 horsepower. So if your machine doesn't have that, then you're going to have to back that down in order to get it within those operating parameters of that machine. And like I said, when you look at catastrophic failure, a lot of times it's hard to be able to pinpoint exactly what went wrong, but those are some things to really kind of look at and do some deducing after the fact to see if that could have been part of the problem. And that covers the application side of things. I'm going to turn it over to Dan Ott and let him talk to a few things on his end.
Good morning and good afternoon, everyone. Like Chris said, my name is Dan Ott. I'm the marketing coordinator at KSPT, and I've been in that role for roughly 4 years. I've worked in the tooling industry, and more specifically for SGS, for the last 15. I currently handle any and all marketing-based communications, both digital and print. Basically, really any communication that gets sent out to our distribution partners or our end users comes from my desk. I currently work here at our HQ, our new HQ in Cuyahoga Falls. And for all of you who've never graced our new campus, I highly recommend you come check it out once COVID restrictions end. So I'll just get right into it. Our website has many different features, for those of you who don't know, that can both educate and inform the end user on not only our industry-leading cutting tools, but also our knowledge of really anything cutting tools. We recommend you do so. You check it out, at your earliest convenience. First off, I'll just go into the Tool Wizard a little bit. That's an application we've had around for quite some time, but has only recently undergone some facelifts. It is a program designed to have the end user input the workpiece material, the cut parameters, and generate both a recommended list of SGS tools to use for that application, and then also the machine parameters like speeds and feeds to use during the operation of that material. And if you haven't already registered, I highly recommend you go to the Tool Wizard at www.toolwizard.kyocera-sgstool.com.
Dan, did we lose you?
You are in mute, Dan.
Do not know how that happened. So one of the next big things that I'll talk about is the addition of the digital catalog. It's a brand new feature of the website where the user can put in any different search facet and find the recommended tool for you guys. You can put in anything from the length of cut of the tool diameter all the way to the material application, and it'll give you a recommended list of tools. You can also do tool comparisons of up to 4 tools at a time. It has cell sheet capabilities. You can select any one up to 4 items and have that tool's attributes and digital assets mailed or printed. Um, it is a really great tool and we highly recommend it. And the last tool I'll talk about is the addition of the case studies and then the brand new knowledge library. The case studies all live on the website, and these are all positive cases generated by our sales and engineering staff. There's currently over 60 that are housed on the website. And those can be searched for via the workpiece material, intended industry, and also by the tool series. These case studies can demonstrate rather the dramatic reductions in overall job cost, hours of machining, and then also show you an increasing in machining efficiencies. Um, and then the last one I'll talk about is the newly created knowledge library, and this is about as brand new as it gets. This is a page of the website that's going to house monthly articles generated by our engineering and sales staff, and can feature any variety of machining topics that you could think of. And then one last thing I'll mention today, guys, is that these webinars and all future webinars and all past webinars will be available via the webinar library of the website. You can also view them if you are a subscriber to our LinkedIn page or our YouTube page. We highly recommend you subscribe if you haven't already do so. That way you don't miss anything that we're up to at the time. So with that, I will hand it off to you guys and see if you guys have any questions for either Chris or myself.
Well, I'm going to jump in and make one comment real quick, kind of just piggybacking off of Dan with the tool wizard and the case studies. This is a really strong resource for anybody to be able to access. I use the tool wizard a lot whenever I have a material that I'm not as familiar with. I'll go in and plug it in whatever hardness configuration it is, and it'll give me a good baseline to start off with. And a lot of times I'll go above and beyond that, but it still is a great option to be able to find some good starting parameters for different materials. And the case studies, I fall back on those from time to time when I'm trying to look at a new application. I'll go back and see, do we have some data on some previous tests that we've done as far as case studies go. So those are available to anybody and everybody. Just use them to the best of your ability. They can be a very helpful resource. And with that, questions? Anybody have any questions? I'm going to drop out of this so we can see the chat. All right, no questions so far. I guess I just did that good a job of covering all that information.
Guys, no doubt. If you guys have a question, please ask. The only bad questions are the ones we forget to ask.
Thank you, Travis, Ernest, Alejandro. Thank you very much. Oh, that's excellent to hear. Yeah, I've seen some of the videos you guys have posted on LinkedIn. Some good stuff going on down there in beautiful South Africa. Thank you, JC.
All right, guys, if nobody has any further questions, please look for this to be posted to the website and our social media later today. And we wish you the best and hope to see you at future webinars.
Thank you. Take care, everybody.
Thanks, guys.